Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our exercises on velocity, speed, and acceleration. Let's just hop right into it. So last time we talked about number 5. We did some exercises on finding the position vector. So we do that by integrating, as well as finding the velocity, speed, and acceleration through differentiating. Um, and we also did some sketching here, where we sketched the position vector, its velocity, as well as its acceleration vector. Okay, so for number 5, we're being asked to again find the position vector. Um, and we're given the acceleration vector as well as a bunch of other information. Where's my number 4? Yeah, okay. So we're gonna find position vector r of t. Uh, and I'm just gonna say given, but basically we have our acceleration vector, which has components. I'm gonna write it immediately in vector form. 11t, e to the t, and e to the negative t. And then we have other information such as my velocity vector at t equals 0 is k. So k is just 0, 0, 1. And then my position vector when t is 0 is j plus k. So to translate, that's 0, 1, 0. That's standard basis vector plus 0, 0, 1. And so we have 0, 1, 1. So I'm going to immediately replace it with that. Okay. So what is the first step? Well, we want to integrate to get velocity, or specifically v of t, our velocity vector. And so to get our velocity vector, we want to integrate our acceleration vector again. So it's really the same step as the one before. And so we integrate each component. So we're integrating the x, y, and z component of our acceleration vector function. And we do it, well, I personally like to do it one by one. So here I see a constant, I take it out just to make my life easier. Now I have a t here, I immediately integrate it. And I add a constant. And then I combine. Okay, my y is, well, this is actually just simple. It's just e to the t. Because if I take the derivative of the natural exponent, it's just the same. So this is one small exception, where if you get the rate of change of this exponential function, it's the same as its position function. And lastly, we have, um, I'll put it here actually. This was, I believe, e to the negative t dt. Yeah, so what would this be? Here I could guess. I could say e to the t, but I know if I take the derivative of e to the t. So here really is just guessing. This is e to the t. Now maybe I can take the derivative of this. So I get e to the negative t times chain rule of this. And so I actually get negative. So how do I cancel this out? Well, I multiply a negative, right? So if I take the derivative of this, so imagine we don't have this. If I take the derivative of that, Well, now I should get negative e to the negative t, chain rule. So we got negative, -1, e to the negative t. Well, here I just get e to the negative t. So that's my answer. It's actually just adding the negative here. Then some constant. Okay, and then from here we find these constants. So let's do that. What information do we have about p? Well, at equals 0, we have 0, 0, 1. So we plug in 0, right? So here we're at our x component. C1 is equal to 0. And so here my C1 is just 0. Now I do my y component. So e to the t, or e to the 0, plus C2 is just 0. So what's my C2? Well, this is 1. So I add -1. So that means my C2 is -1. And lastly, I have negative e to the negative t plus C3 equals 1. And so, okay, I change this to a 0. I get -1 here. So what do I do here? Well, C3 should be 2, right? Because 2 minus 1 is 1. And there we have it. Now I got my vector. My velocity vector. Done. Let me copy. Okay. I have 11t squared over 2 plus C1. So plus 0, plus 0, so that's nothing. E to the t plus, no, it's -1. Because my constant 2, my second constant is just -1. And lastly, negative e to the negative t plus C3, so plus 2. And done. A little check mark. Now we integrate this again to get my position vector. So my r of t. So what I'm saying in math terms, my r of t is just the integral of my v of t, of my v of t. And from here, okay, we're integrating each components. Okay, I can rewrite this a little bit better because the thing when integrating is I want to eliminate, or not eliminate, I want to format my numbers in such a way that makes it easy to integrate and find the derivative. Okay, this one stays the same. That doesn't matter. This one I could maybe put my 2 in front. 2 minus e to the negative t. Yeah. Just so that doesn't consume more space because if I add the plus, right? And I forgot to I forgot to integrate. Okay, let's integrate. Okay, then last one. Okay, now we integrate each of these components one by one. So let's start off with this. Well, I can take out my 11 over 2. I can now take the antiderivative of this. So I got t cubed over 3 plus some constant. And then here I can just multiply. So I have 11t cubed over 6 plus c1. Done. Now I look for the next one. E to the t minus 1 dt. So I can actually separate this. I don't want to. I'm fine. I got e to the t minus t plus c2. As easy as that. Then the last one, 2 minus e to the negative t. Well, here I integrate. So this is 2t. How do I integrate this value? Okay, let's make it easier. So I say 2 dt. I subtract e to the negative t dt. So what is this? This is 2t. So that's easy. What is this? Minus this one. Um, oh, we did this before, actually. There we go. Negative e to the negative t. Yeah, so minus this one. And so that means there's just a plus. So it's plus e to the negative t. And then that's it. I add a constant. Now I find my constant. So we need to use our given info on R, which is at time 0, these are our components. So let's make use of that. So at time equals 0, I keep saying time, at t equals 0, we should get the corresponding x, y, and z components. So let's start with our first one. So we have 11t cubed over 6 plus c1 is equal to what? What is this equal to? It's equal to 0. We change this to a 0. Well, now c1 is just 0. Okay, let's do the next one. We do e to the t minus t plus c2. This is equal to what? It's equal to 1. I say this is 0, this is 0. So this is 1 minus 0 plus c2 equals 1. So this is 1 plus c2 equals 1. This is 0. c2 is 0. Right? Last. Oh, there. There you are. 2 times 0 plus e to the 0 plus c3 is equal to 1, right? Yeah. So this is 0 plus 1 plus c3 equals 1. Well, this is just 0. So I completely get rid of my constants. So my r of t is just these guys without the constants. 11t cubed over 6 comma 2t plus e to the negative t. And then, oh, I completely missed this. E to the t minus t first. And then my 2t plus e to the negative t. And there we go. Done. That's my position vector. Okay, let me type it in, see if I get 11 over 3, I believe. E cubed. Oh, that was 6. Comma e to the t minus t, comma 2t plus e to the negative t. Done. Okay, yeah, that looks about right. I'm assuming it's right. Let's see if we get it. Nice. Okay. And we'll do one last one before we take a little break. Okay. So here we're actually given the position function. Ah, what is this handwriting? Of a particle is given by r of t. Let's do in another line. R of t equals t squared comma 3t squared, not 3t squared, 3t comma t squared minus 16t. Okay, these are x, y, z components. That's our position vector. Oh, when is the speed a minimum? So how do we find that? We can take the derivative. I guess we can find the speed function, but then how do we determine if it's a minimum, right? So when is it a minimum? Let me just quickly check how to do that. Okay, we take a derivative. We find our we find our speed, which is a distance. Minimize the square of this. So we square it, we take its derivative. T is equal. Oh, it's asking when. So it's asking for a t because it's asking when. Uh, so the derivative we put it to 0. We get 4. We take the second derivative. What does that tell us? Oh, okay. Let me just write that step by step. So to find when is the speed of a minimum, we're basically finding a t. We're finding t. We're finding t here, right? So the first step is obviously find speed. Or if you want to be even more specific, to find speed, we need velocity. So we find velocity. And let's make it specific, specifically v of t, right? And so if we find v of t, we take the derivative of my position vector. And so this is 2t, 3, 2t minus 16. Then from there, we find speed. And so we take the absolute value or magnitude or length of my velocity vector, and then we put everything here squared. Right? And so here we got what? We got 4t squared plus 9. I could simplify it. Okay, maybe I'm going to expand this. So 2t minus 16, we're going to do it twice. So here I'm just expanding. Here I get 4t squared. Here I get minus 16 times 2t. So that's what? 16 times 2, that's 32. Minus 32t minus 32t. So minus 64t. And then here we add 16 times 16, we get 256. Okay, so we add it to here. 4t squared minus 64t plus 256. And we can simplify this even more. So here we get 8t squared. Here we get 256 added to 9. So we get 265. And there we go. Now I just replace it here. The simplified one. Cool. Okay. Okay. And then from there, once we find that speed, now we want to minimize the square of the speed, right? So we want to find the minimum. We're looking for something like a derivative here, maybe. Basically, if we want to minimize the speed, well, here we're given a speed, right? If we think of it as a real valued function, and then what we want to do to minimize or to find the minimum is we take its derivative, right? But apparently there was another way to do it here, which was to take its square. Then once we take its square, we can take its derivative, set it to 0, and then find that time. So apparently we can do that. So let me minimize speed. So that's a thing. Yeah. If you want to minimize the speed, then you want to do this. Because taking derivative is a hassle. So I could just square my speed. And then I could take its derivative, right? So if I take its derivative, I don't know, let's do d dt of this thing. So I get 16t minus 64. And I set my derivative exactly equal to 0. Am I doing it right? Yeah, I'm doing it right. I think. I set it to 0 and I get a time. So here my time is 4, right? If I divide 64 by 16, yeah. So my time here is 4. And then from there, we take its second derivative. So I'm pretty sure there was a way to write this. I just forgot how to do it. I think it was, oh crap. How was it written again? I think it was like this, and then then like that, like that. So the second derivative of this thing, well, we just take its derivative again. We get 16, which is greater than 0. So this means concave up, since the second derivative is greater than 0. And so if it's a concave up, right, goes up, then anything we put here is a minimum. And so here I actually kind of found it already. This was just a proof saying, okay, we know it's a minimum. Because even though we found the tangent, right, where the derivative is 0, we still have to prove that it is indeed a minimum. Because I don't know, this could be a maximum. So when t is equal to 4, and that should be it. Yep. Okay. That's it for now. I have like what, 4 more examples to go. But yeah, for 5 more examples to go. 7, 8, 9, 10, 11. Yeah, 5 more examples to go. But yeah, I hope you guys enjoyed, and I'll see you all in the next one.